In this session, we'll be trying to solve this steady state heat transfer problem. So there is this induction furnace wall, which is made up of three different material, whose thermal conductivities are given as K1, K2, and K3. These are the values. On the left hand side, the wall is insulated. That is what it is shown here. The temperature here is 600 degrees Celsius. On the right hand side, there is a convection effect, and for that, H is given as 45 watt per meter square Kelvin, and the ambient temperature is given as 30 degrees Celsius. Each of these lengths are given here in terms of centimeters. And then what we are supposed to do is we are supposed to determine the nodal temperature. Of course, we'll be solving this problem now on ANSYS Workbench. But before that, just to verify our results, what I have done is, as usual, I have solved this problem, assuming it to be a one-dimensional problem. Here I have modeled this entire problem into three with the help of these three elements: element 1, element 2, element 3, and these will be my nodes 1, 2, 3, and 4. So what do we do? How do we proceed? Is we start with the heat conduction matrix, stiffness matrix for heat conduction. So the stiffness matrix for heat conduction is given as this: AK by LE 1 minus 1 minus 1 1. We are all aware of this matrix. So the moment we start substituting the values, we'll realize that the cross sectional area is not given to us anywhere in this problem. So what I have done, I have assumed it to be of 1 meter square or a unity. All right, so area is 1. K for the first element, that is for this element, K1 is given as 8.5 watt per meter Kelvin. So that is what I have substituted here, 8.5. And the length is given as 25 centimeters. So in terms of meter, it will be 0.25 meters. And then this is 1 minus 1 minus 1, 1. After multiplying, you will get this matrix. Similarly, for element 2, we will end up getting this matrix. For element 3, we will end up getting this matrix. But then this is not all. Okay, we can frame more global stiffness metrics for conduction here at this stage. But then what is happening is at this node, at node 4, there is convection that is taking place, right? Heat is getting dissipated to the surrounding or to the air, which has an ambient temperature of 30 degrees Celsius. Now that can be modeled by using our convection matrix, and the convection matrix for end effects is given as this, that is HA0001. Now H is given to us, the value of H is 45 watt per meter square Kelvin. I have substituted here. Again, area is unity, which is what we have assumed, and then finally we'll get this. Now this is applicable only to the node number 4 or at element 3, and therefore the global stiffness matrix will look somewhat like this. So this will be node 1, node 2, node 3, node 4. So this is applicable only at node 4. Finally, global stiffness matrix is only for the considering the convection effect. So the total global stiffness matrix will be that of conduction plus convection. So what we'll have to do is this 45 we'll have to add to this 2.66, and finally we'll get the global stiffness matrix as this. Then the force vector, because of the convection, since there are free convection that is taking place at this end, therefore there will be also a force vector there at that node, and that is given as AHT infinity 0, 1. So if I start substituting all the given values, that is area is 1, H is 45, T infinity is 303. By the way, here the temperatures which are given are in terms of Celsius, right? But while incorporating that in this, we'll have to convert it into kelvins, because you see here the K values or H value is given in terms of per Kelvin. So I'll have to obviously convert this 30 degrees Celsius into Kelvin. So you need to just add 273 to your given temperature in Celsius. And if I do that, I'll get this as my force vector. Again, please remember this is applicable only for node 4, and for other nodes it will be 0. So after this, if I write my equilibrium equation, I'll get this as my equilibrium equation. Of course, at node 1, it is given that the temperature is 600 degrees Celsius at this node, right? So if I add 273 to this to convert it into kelvins, I'll get this as approximately 873. So that 873 will be taken as a boundary condition here. I cannot solve this matrix as it is, right? I need to apply boundary condition just to avoid that singularity property of this matrix. You all are aware of it. So once I substitute this value as 873, and then after adjusting all these rows and columns here, ultimately I should be able to get this T2 as 846.25, T3 as 664.35 Kelvin, and finally T4 as 323.21 Kelvin. So this is the way how we can use our 1D approach to solve 1D FE approach, finite element approach, to solve this 1D heat conduction problem through composite wall. Now let us switch to our ANSYS and see how to deal with this problem. So this is how our ANSYS Workbench project schematic page looks like. So we need to now perform thermal analysis, right? And it is a steady state thermal analysis. Let me remind you, the temperatures are not changing with respect to time, and therefore it is a steady state thermal analysis. If your temperatures are changing with respect to time, you will have to go for transient thermal analysis. So this, in this case, our case is a bit simpler. So we'll go for steady state thermal analysis. The first thing is we need to obviously define the material. We have three different types of material. So what I will do, I'll right click on this engineering data and I'll say edit. I'll click here to add a new material. I'll say material A, mat A. Just you can give any name. I'll say material A, that is for first material. And then I know its thermal conductivity, right? The thermal conductivity for first material is given as 8.5 watt per meter Kelvin. Now you need to be careful with these units, all right? So by default, always the unit will be watt per meter degree Celsius, but the value which is given to us is watt per meter Kelvin. So choose this appropriate unit, and then you can enter this value as 8.5. Similarly, I will have to now define mat B, right? So this is my second material. I'm calling it as material B. Again, same isotropic thermal conductivity. Be careful with the unit. Change it to watt per meter Kelvin, and the second value is 0.25. So let me enter this value as 0.25. And similarly, third material has a thermal conductivity value of 0.08 watt per meter Kelvin. So this will be 0.08. Okay, let us just verify once again. Material A 8.5 watt per meter Kelvin, material B 0.25 watt per meter Kelvin, and material C is 0.08 watt per meter Kelvin. I think we are done with this defining this engineering data or the engineering material. So I can close this tab. Let us go to geometry. I will be creating this geometry using design modeler. You can even create it as with your space claim, whatever you are comfortable with. You can create this geometry. Now what I'm going to do is I will sketch this. I'll consider this to be my x-axis. Okay, so the cross-sectional area, this area of 1 meter square, I will have to sketch it on YZ plane so that I can extrude it along the x direction. So what I mean to say is what I'm going to do is I'll sketch my cross-sectional area on YZ plane. Okay, so I'll go to sketching. In the meanwhile, see, if I just draw a rectangle from this point to this point somewhere here, I'll end up getting a rectangle of side around 20 meters, but I don't want that big rectangle, right? So what I will do, I'll just scroll my mouse, and then I will zoom out, right? I will zoom in. So approximately this should give me the, if I now draw one rectangle from this point to around this point, it should give me an approximate length of 1 meter, right? So let us see, from this point I will approximately draw one rectangle here. In fact, it should be a square, right? It is a 1 meter square area. So what I'm going to do, I'll go to the dimension, I'll click on general, I'll take these sides, and then I'll change this dimension as 1 meter and 1 meter. All right. So now I have sketched this square on YZ plane, and then I will have to extrude it along the X direction. So what I need to do is I will have to go to create, click on extrude, and then just check here the distance by which I need to extrude it. Right. This length is how much? It is 25 centimeter or 0.25 meters. So I need to enter that. In place of 1 meter, I need to enter 0.25 meters and then say generate. So this is my basically the first wall. All right. I mean the first part of that composite wall. Okay, now what I need to do, I need to now sketch the second wall on this face, right? This face is not readily available here. I only have the three planes XY, ZX and YZ. Now again, if I choose this YZ plane, you'll have to again sketch on the YZ plane and that will overlap on this body. I don't want that. I want to start my new sketch from this face. So what for therefore what I will do, I'll go to the face selection. I will select this face and then I'll go here and I'll click on new plane. And then I will say generate. Now what has happened is a new plane is been generated here on this plane. So now my second sketch, I will start sketching on this plane. So again, I will align it to my screen and then I will go to sketching. I will go to rectangle. I will select this plane. Okay, you need to make sure that this P is appearing here in the screen, right? It is a inverted P kind of, right? So from this point to this point, all right. So I have nicely now created one more rectangle on this plane, new plane, and then I need to do same thing now. I'll have to go to create. I will click on extrude. All right, just say apply, and but the distance by which I need to extrude is how much? This L2 is 5 centimeters. So that is basically 0.05 0.05 meters. Okay, but the important thing that you need to observe here is this add material, you need to change it to add frozen. By this time you must be aware what is the difference between add material and add frozen, right? I have explained it in detail in our one dimensional bar problem, so you can again go to that video and check what is the difference between add material and add frozen. Once I do this, again I have to click on generate. So now I have been successfully able to generate my second wall. Again, what I will do, I will select this plane. I will click on new plane and then I will say generate. Now the new plane has been generated on this plane. Okay, so again I will align it to my screen. I will go to sketching. I will go to rectangle. I will select this point. I'll make sure that P is appearing here, inverted P, and then from there I'll make sure that again here one inverted P is appearing, and then finally I will complete this rectangle. So after that, again same story, go to create, extrude, say apply, change this add material to add frozen, and then this 0.05 I need to now change it to 0.03, right? So this will be 0.03. Okay, and then say generate. So I have been able to generate now all these three different walls. So it will look somewhat like this, right? I mean, it should look somewhat like this. Okay, so this is my first wall, this is my second wall, and this is my third wall. So only last step what we need to do is we need to select all of these three. You can press Ctrl and select all of these three bodies, and then right click and you can say form a new part so that we can maintain the continuity. So anyways, at this stage, what I will do, I'll just minimize this. I don't want to close this yet because if there is any changes to be made, I'll come to this tab later on and I will do the remaining changes. So I think the modeling part is done here. I'll go back to my project schematic and we'll now go to model. So how to do that? Right click and then say edit. So after some time, depending upon your processor and RAM, it will open this page. Okay, steady state thermal mechanical, and then here what you need to do is first of all you need to go to the geometry, go to the part, go to the solid, and then as we know by default, ANSYS will always assign structural steel to any material. But for this first block, we need to assign our first material, that is material A. We have created these three materials, right? For the second solid, what we are going to do, we'll assign material B, and for the third solid, we will assign material C. So this is how we'll assign the three different materials to these three solids. For first solid, it is material A. For second solid, it is material B. For third solid, it is material C. Now, once I assign this material, what we'll do is we'll just right click on the mesh and we'll say generate mesh. Let us see what is the default mesh that we are getting here. All right. So we are getting pretty decent default mesh. All our chord elements, all right. The proper brick mesh has happened here, although this was by default, but we got a very decent mesh. if I go to statistics, I can check here the number of nodes and element. The thing is, I'm using here a student version ANSYS, so I think I have a limitations of around 30,000 nodes. So what I will have to do, I will have to drop this element order to linear. I cannot afford to mesh this now elements with a higher order element or a quadratic element. All right. The difference is that if you go with a higher order element, you can see here that you will get a node in between this, right? This nodes, obviously it will be there, but you also end up getting one node in between. Can you see this, right? But obviously it is good for obtaining a very accurate results. But in this case, since I have limitations, what I will have to do is I'll have to change the element order to linear, and I cannot leave it to program. Okay, so I will change it to linear, and then I will right click and I will say generate mesh. Of course, if you are using a full version ANSYS, you can obviously go with a quadratic element. There shouldn't be any problem. Now it has reduced to see only 10,933 nodes. So what has happened, just if I show you here, now I don't have any node in between. Can you see this? If I click somewhere in between, the node is not appearing, because what program has done is program has dropped the mid nodes. Okay, so it has changed the order from quadratic to linear. All right, so I had to do this because of these limitations. Anyways, if you are using a full version ANSYS, you need not do that. So what I can do here is, probably these nodes are a few very less, right? So what I can do is I can go to default, and then here under element size, what I can do is probably I can go with around uh, 25 size elements. Okay, let us see how many elements there it is creating. Okay, how many elements and how many nodes. So here with a 25 element size, I can see here that it has created 25,000 nodes. All right, and since my node limit is up to 30,000, I can easily solve this problem. Again, I am repeating, if you are using a full version ANSYS, you did not bother about this or the higher order. You can very well proceed with higher order elements. All right, but since I have limitations here, I am going changing it to linear order elements, and I am that is how I am controlling my node numbers. Okay, anyways, so this look a pretty decent mesh. Let us go to the boundary conditions, which is the most important thing for us, right? So the boundary condition here is, at this wall I have a temperature of 600 degrees Celsius, and this, let me remind you, in thermal problem, this is not the fixed boundary condition, but this is the insulation. All right, this is the insulation that is provided. So first what we'll do, we'll provide an insulation on this wall. And how to do that? You can on this wall, what you can do is, you can go to environment, and then you can go to this heat, and then you see here you have an option of perfectly insulated walls. Okay, so you just click on that and then select this surface. All right, you need to select this surface, say apply, and that's it. Okay, so you have applied a perfect insulation on this wall. All right, so after this, now what we can do is, we need to apply the temperature boundary condition there, right? So the temperature is 600 degrees Celsius. What to do now is to go here at temperature, click on this wall, say apply, and change this temperature magnitude to 600 degrees Celsius. Please be careful with the units. All right, since here there is a degree Celsius, I directly entered the value as 600. Okay, if it is for you, if it is Kelvin, you'll have to add 273 to this 600. So after this, what I can do is, probably I can go to the third boundary condition, that is the convective effects on this wall. There the H is given as 45 watt per meter square Kelvin. So what I need to do is, I need to go to now convection. Okay, I need to apply the convection on this wall, say apply, and then the value of H is how much? It is 45 watt per meter square Kelvin. All right, but here it is watt per square degree Celsius. So what you can do, you can probably go here, or you can go to say units, whatever is comfortable for you, and then change this to, first of all, to meters. So I will get this as watt per meter square Celsius, but again it is watt per meter square Kelvin, right? So again, you can go to units and then change this temperature to Kelvin. So finally, now here I am having the value of watt per meter square Kelvin. All right. So because of this, now I can easily directly enter this value of H as 45. So here the H value I'm entering it as 45, and the ambient temperature here is given as 30 degrees Celsius. Now again, here there is a Kelvin unit, so I'll add 273 to this, so it will be approximately 303, right? So 303 Kelvin. Okay, so why I'm entering here 303 Kelvin, because this is Kelvins, right? And they have given us temperature in terms of Celsius. So to this 30 I have added 273, so that is giving me 303 Kelvin. Okay, so I think we are done with the boundary conditions here. If I just click on the steady state, it will show me all the boundary conditions that I have applied, right? Heat is 0 here, 0 watt. That means it is a perfectly insulated wall. Then the temperature is 873.15 Kelvin. It has converted that 600 degrees Celsius into Kelvin. So ANSYS is taking 273.15 as a Kelvin term. That is okay, it shouldn't make much difference. And then finally the convection here is 45 watt per meter square Kelvin at 303 Kelvins. Okay, so all these boundary conditions, we are done with all the boundary conditions, and I think at this stage we can solve this problem. Right, so what we'll do is we'll right click on the solution and we'll solve this. uh, if you are really working on some important project, please don't forget to save it before actually solving the project. All right, there are chances that your software might crash at this stage if something goes wrong. Okay, so always a good practice it, you need to always save your project before actually solving your project. All right, so ultimately here luckily we have not encountered any error. Okay, neither our software has crashed, so good for us. So at this stage what we need to do, right click here, insert, go to thermal and then say temperature, and then right click and then say evaluate all. So if I do that, this will basically give me the temperature distribution across the wall. All right, you can see here we are getting a nice temperature distribution across the wall. Since I want a nodal temperature, what we can do is we can right click here, say insert, go to probe, and then you can take temperature and you can place this probe here at different points, whichever at all the point of interest. Or else what you can do is the other way is you can go to say solution probably, or here on the temperatures and go to results, and then you can select this probe and you can just click here at different locations. Okay, at this node, at this node, and then our next node was around this, right? So any node along this line, all right, and then finally at this node. So these are our temperature distributions at different nodes. Okay, the nodes, which are the nodes, these nodes 1 2 3 4, you can choose, select the node anywhere along this line. All right, and that will be I mean you will get a same temperature distribution. You should get a, hopefully you should get a same temperature distribution there. Okay, so our values were T2, that is at this node, second node, I was getting it as here 846.25. Let us check now what we are getting here in ANSYS. So here I am getting it as 846.39, and here I was getting it as 846.25. So pretty close, right? That because that we have skipped 0.15 factor while changing from Celsius to Kelvin, there might be some difference there, but 846.25 and 846.39 is pretty close value. Here on this wall I'm getting here in ANSYS it is 664.42, here it was 664.35, pretty close. And then finally at this last node I'm getting a temperature is 323.22, and here it is 323.21. Okay, so this is how you can perform your steady state thermal analysis in ANSYS Workbench.